we already see that what is the pure bending. So if I just make a diagram for the pure bending, how the pure bending will look like. So let us say that this is a member AB. The line shows is the longitudinal axis. Suppose this is the member or beam AB. With this beam, I attach a lever, this CD. CD is a lever which is attached with this beam AB, and it is welded here. That means the member AB and CD cannot move relative to each other. Right? That is important, that there is no relative motion between the member AB and CD. CD will act as a your lever, or it will act as a integral part of the beam AB. So from CD I applied two loads, that is this P1 and in this direction it is P2, right? And I will say that the magnitude of P1 and P2 are same. P1 is equal to P2 is equal to P, right? The magnitude of both the loads are same. As from our earlier discussion, this vertical axis is Y, longitudinal axis is Z, and I show the cross section of this AB. The cross section of AB will be like this. It is a rectangle of depth D and width B. So the cross sectional axes are Y and X axis. This is the depth D and this is the value of Y max. We'll see what is the meaning of Y max in your pure bending chapter. This is just a discussion. So if I say that there are two loads P1 and P2 here, the magnitude of both the loads are same, but the direction of both the loads are different. So if I say with respect to AB, if I see that this is the longitudinal axis of AB and the load, this P1, if I talk about P1, the P1 is a load which is parallel to the longitudinal axis but do not pass through it. So the load P1 is your eccentric, this is eccentric, and if this is the cross section of B, it is eccentric tensile load, right? It is a eccentric tensile load with respect to AB, and P2 is also the force which is parallel to the longitudinal axis but do not pass through it. So P2 is also eccentric axial load. And which type of load? If this is a cross section, it is a compressive load. So it is eccentric compressive load with respect to AB. Or if you can say, if just for your understanding, for this CD, if you see, this is the longitudinal axis of CD. This load is perpendicular to the longitudinal axis and pass through it. So P1 and P2 are the transverse shear load for the member CD, right? So if I say that because of this load P1 and P2, the loads are of different direction. One is in the tensile nature, one is the compressive nature, and there is a distance between them, that is CD. So the load P1 and P2 will give us a couple in this direction. The P1 and P2 will give us a couple in this plane of this board, right? This P1 and P2 will give us the couple in this YZ plane, and the couple in this YZ plane is along the longitudinal axis. So the couple given by this P1 and P2 is in the YZ plane, which is along the longitudinal axis and perpendicular to the cross section. So the couple given by this P1 and P2, whose value will be equal to load into perpendicular distance, that is CD. So this couple will be a bending couple, right? It will give, this P1 and P2 will give us a bending moment. The value of that bending moment is your P into CD. So if I draw a free body diagram for this member AB, so let us say this is the member AB, and at B we have a bending couple, right? Again I am saying why bending couple, because this couple is in this plane of board, and this plane of board is along the longitudinal axis. This plane of board is perpendicular to the plane of cross section, so it will give us a bending couple. So the bending couple given by this load P1 and P2, this value is P into CD, right? This value is P into CD. This is the free end of the beam, this is the fixed end of the beam. We know if I applied a force, if I applied a bending moment in this direction, then the fixed end will give us a reaction to it. Every force is a action and reaction. For every action we have a reaction, and that is also of opposite nature. So if I try to bend this system in this direction, in this clockwise direction, so the reaction would be in the anti-clockwise direction, right? Reaction would be the same of magnitude but of opposite direction. If this bending couple, that is P1 into CD, will bend the beam AB in clockwise direction, then the reaction on the fixed end will be the same magnitude of bending moment, that is P into CD, but in reverse direction, that is anti-clockwise direction. So this is the free body diagram of AB. Now we want to know what is the bending moment at a section X from the free end. I am taking a section XX which is at a distance of X meter from the free end, and I want to know what is the bending moment at this section X. So please note this will be discussing in each and every chapter, and this will be an important concept. So load at any section, if you want to calculate the load at any section of a beam or of a shaft or of any member, is equal to the algebraic sum. The meaning of algebraic sum is, as per sign convention, you take positive, which as per the sign convention, if the load is positive then you have to take positive, if the load is negative then you have to take the negative. It is the algebraic sum of all the corresponding loads. This is important. Corresponding loads means, if you want to calculate the shear force at any section, then you have to see for only shear force. If you have to calculate the bending moment, then you have to see for the bending moments only. If you have to calculate the axial load, then you have to see the axial loads only, right? Corresponding load either on the right hand side or on the left hand side of the section, right? So load at any section is equal to the algebraic sum of the corresponding load either on the right hand side or on the left hand side of the section, right? So if I say that at any section XX, if I want to calculate the bending moment at this section XX, then I am saying the bending moment at a section XX is equal to the algebraic sum of all the bending moments either on the right hand side or on the left hand side. So if I take on the right hand side, then from this section XX, if I take, then on the right hand side there is only one bending moment, that is P into CD, and that bending moment is in clockwise direction. And as per our sign convention, the bending moment on the right hand side, if it is clockwise, then we have to take minus, then it is a negative. So the bending moment at section XX is minus P into CD, right? Or if you take the section XX and if you are seeing on the left hand side, then on the left hand side bending moment is only one, that is MA, or the reaction, which is also equal to P into CD. But now on the left hand side, if the bending moment is your anti-clockwise direction, then it is negative. So the bending moment at section XX will be equal to minus P into CD. And if you see in this relation, the bending moment at any section X is independent of X. The bending moment at any section from the free end is independent of its distance from the free end, and or you can say this P into CD is constant. So along the length of AB, the bending moment will remain constant. So it is a pure bending. In pure bending, we have the bending moment constant, and other forces, that is twisting moment, shear force and axial load, will be equal to 0. All the other forces will be 0. Only bending moment must be there, and this bending moment will be constant throughout the length of the member or your beam. Now, if you want to calculate what is the bending stress in this case, the bending stress formula is your bending moment upon section modulus. This is your bending moment upon section modulus. We'll say that section modulus is your moment of inertia about neutral axis divided by the length of the maximum length of the fiber from neutral axis, right? We'll see it later on how to calculate INA and Ymax. But right now, if you want to see that this couple is in this plane of board, and this couple is about the axis XX, right? About this axis, and that axis is XX. So here I have to take IXX in this case, and IXX moment of inertia for a rectangle is, for x-axis, this is BD cube upon 12. BD cube upon 12, right? Or if there is a bending moment which is about the axis YY, then IYY will be equal to your dB cube upon 12, right? This moment of inertia, basic moment of inertia, you know how to calculate for different axes. And if you want to calculate the moment of inertia about Z axis, then you have to use the perpendicular axis theorem. That is, the moment of inertia about one axis is equal to the sum of moment of inertia about the other two mutual perpendicular axes, right? This is the perpendicular axis theorem for the moment of inertia. So this is how you can calculate, and we'll see how to use these formulas of calculating bending stress in our pure bending chapter, right? So this is how you can see that this is a pure bending case. So from here you can say that the pure bending is possible when a member is subjected to two equal and opposite eccentric axial load. These are the eccentric axial loads. So you can say that pure bending is due to two parallel, equal, opposite eccentric axial load, right? If I write here that, if I write pure bending, just for your more concept, that pure bending is from two parallel, equal, opposite, right? Two parallel, equal, opposite eccentric axial load, right? They must be parallel, they must be opposite, they must be equal, they must be eccentric axial load. Then only pure bending is possible. Now if the next is your pure torsion. We already see what is the pure axial loading, what is the pure bending. The last one is your pure torsion or pure twisting moment. So we can say that when a member is subjected to two equal and opposite couples which are acting in a plane parallel to cross section, right, or perpendicular to longitudinal axis, and magnitude of twisting moment will remain constant throughout the length of the member, then you can say that the member or the shaft is subjected to pure torsion. When the couple is your equal and opposite, which are acting in a plane perpendicular to the longitudinal axis or parallel to the cross section, and the magnitude of twisting moment will remain constant throughout the section or throughout the length of the member, then you can say that the shaft is subjected to the pure torsion. Now suppose we are considering one shaft, that is AB. This is a shaft. The cross section of this shaft is a circle. This is a circular shaft. The diameter of the shaft will be D. Right? The axis we know, this is the Z axis. The axis, this vertical axis is Y, and the other axis on the cross section is X, and this axis is Z. This is cross section, right? Don't confuse with this. This is cross section. This I draw when I see this shaft from this plane. This I draw like this. This is the cross section. This is the cross section of beam, and this can be drawn by seeing this view of the beam, and I just put it here, right? This is the cross section. I just rotate it and draw it here. So this is the Y axis, this is the X axis. So I can write this is the Y axis, this is the X axis, right? You know how to draw the diagrams, or you can draw the projections, right? Now from this shaft AB, this is a shaft. From this shaft AB, I attach a lever, this which is welding here, right? This is a lever CD, and from CD I applied two load in the plane perpendicular to the plane of board. These loads are not inclined, please don't confuse. These loads are along the axis XX, right? These loads are like this, in this plane. These loads are in this plane, in this direction and in this direction. These are not in the plane of board. These are not inclined forces. These are in the plane, or these are in the perpendicular to this plane of board. So because this is a 2D and we have to represent the 3D diagram, so I am using this inclined lines, right? So these forces are like this, from C in this direction, from D in this direction, right? So if I say that this force is like, this is the force, this is the longitudinal axis of AB. So this force P1 is perpendicular to AB but do not pass through it, or this force is perpendicular to the longitudinal axis but do not pass through it, and the magnitude of P1 is equal to P2, which is equal to P. So you can say for the member AB, these loads are eccentric transverse shear load. These loads are eccentric transverse shear load. The case would be like this. If I make you more understanding, this is a shaft, the lever is attached to it, right? So we are applying one force in this direction, P1, and one force in this direction, that is P2, right? The tip of this marker will show the arrow of the force. This is P1 and this is your P2. So this P1 and P2 is equal and opposite, and it will give us a couple. This P1 and P2, this is the P1 is in this direction, P2 is in this direction. So P1 and P2 will give us a couple in this plane, and the plane of this couple is parallel to the plane of cross section, or you can say the plane of this couple is perpendicular to the longitudinal axis. So these P1 and P2 will give us a twisting moment, because the twisting moment is that moment when the couple plane is parallel to the plane of cross section and perpendicular to the longitudinal axis. So this P1 and P2 will give us a twisting moment whose value will be equal to load into perpendicular distance, that is P into CD, right? And it will give us your twisting moment in this direction. So there must be a reaction at this point A, which is also equal to your, this is reaction moment, which is also equal to P into CD. P into CD. And if you want to calculate what is the twisting moment at any section XX from the free end, so you can say whether it will be all the algebraic sum of twisting moment only, either on the right hand side or on the left hand side. So we can say that if it is on the right hand side, so this is your Tm, which is equal to P into CD, and it is also independent of X and it is constant. So you can say because of these two equal opposite eccentric transverse shear load, we are having a constant twisting moment, that the value of that moment is P into CD, and which is constant along the length of this member. So this is the case of pure twisting moment, and you can say for pure twisting moment, your twisting moment will remain constant. Other forces like your bending moment, shear force, axial loading, all these forces are zero, right? So this is the case of your twisting moment, pure twisting moment, and the shear stress by this twisting moment, that is T, is the twisting moment divided by, this is polar section modulus. This is polar section modulus. You just remember one thing, if you see that I am here using a symbol sigma. Sigma is a symbol used for normal load, normal stress, and I am using the symbol tau here, which represent the shear load. And I already say that the bending is a normal load which will give us a normal stress, and twisting is a shear load and it will give us a shear stress. So don't confuse with it, why I am using sigma here, why I am using shear or tau here. This is a shear load, this is a normal load. So this is the case of your pure torsion. So we can say that pure torsion is possible when a member is subjected to two equal opposite eccentric transverse shear load. When any member is subjected to two equal opposite eccentric transverse shear load, then that member is under the pure twisting or pure torsion. So this is the case of pure torsion. We already covered pure axial and pure bending. Pure means only that force is there. If we are talking about torsion, then only twisting moment will be there. If I am talking about bending, then only bending moment will be there. If I am talking about pure shear force, then only shear force will be there. If I am talking about pure axial loading, then only pure axial load must be there. The rest of the forces will be zero. Then we can say that member is in the pure axial or pure bending or a pure torsion.